Bedford Science Cafe. Can everyone hear me in the back there? How are we doing? This is as loud as it goes, as I understand it. So how about that? Is that a little bit louder? Can we all, in the way back, can you hear me in the way back? We're good? Okay. If we're not speaking directly into the microphone, please do not hesitate to let us know. My name is Miles Grant. I'm a member of the steering committee of New Bedford Science Cafe. We thank you so much for coming out tonight. This is one of our largest turnouts ever, and maybe our largest turnout since we've been here at last round. Yeah. We always want to thank Last Round for hosting us here. We'd like to thank our staff. They do an incredible job. It's really hard on a Tuesday night where, you know, we all just come piling in and put our dinner orders in, and they need to get 100+ dinner orders out in a very short period of time. So please be patient with them if your order takes a few minutes to come out. But honestly, they've been doing a great job lately of getting stuff out very fast. So thanks to the staff here. Our speaker tonight is Grant O'Reilly. He's a fellow member of the steering committee. His topic tonight is going to be the Science of Oppenheimer. It was the Oscar, the Best Picture winning film now about the Manhattan Project. But Grant, some people haven't seen the movie, so please don't spoil the Manhattan Project for us tonight, if you could. I said don't spoil it. Grant is an experimental nuclear physicist and professor of physics at UMass-Dartmouth. He has his Ph.D. in nuclear physics from the University of Melbourne in Australia. His research interests are the area of intermediate energy photonuclear physics, right? With special emphasis, on few-body nuclear physics and pion photo production. Anybody have a hobby? And again, he's one of the members of the steering committee of New Bedford Science Cafe, so he's a regular around here. And always say hi to Grant if you see him. Again, his talk tonight is the Science of Oppenheimer. Grant, take it away.
Thank you, Miles. So I promise I won't give away the ending. So Christopher Nolan's film Oppenheimer, it was about what happened to Oppenheimer after the Second World War, and really it was about the US politics of that era. But its backstory was the development of the atomic bomb, which Robert Oppenheimer oversaw as director of the Los Alamos lab. So, as Miles said, I'm an experimental nuclear physics. And the field of nuclear physics is barely 100 years old. It began in 1910 with a New Zealand physicist, Ernst Rutherford, and he did measurements of alpha particles. They come from natural radioactive materials, and how they scattered off very thin gold. And this, with an elegant experiment, demonstrated that the atom consisted of a tiny nucleus, about 100,000 the size of an atom, which is tiny to begin with. But this tiny little nucleus held almost the entire mass of the atom. Most of an atom is literally empty space. And over the next few decades, further experiments were done. One of them, or many of them, revealed the nucleus itself was made up of positively charged protons and electrically neutral neutrons, which are very important to this story. So as I said, the next 2-3 decades, there were many, many experiments in this new field of physics to study the nucleus. And understanding these experiments depended on the then new theory of quantum mechanics. And quantum mechanics just deals with how objects as tiny as protons and neutrons behave. And it's weird. Anyone who studied quantum mechanics goes, this is weird. Then they study it more and they go, this is freaking weird. And in fact, it was the quantum mechanics and the theory where Robert Oppenheimer actually did his research. So he was not an experimentalist at all. He just was a brilliant organizer. So 1910, nuclear physics begins, experiments are done with natural radioactive materials, and then scientists, physicists developed particle accelerators. And these could produce energetic beams of protons, little parts of the nucleus, alpha particles, and importantly, neutrons. And neutrons are important because they're electrically neutral, so they can get very close and in fact enter another nucleus and change that nucleus. So neutron studies were sort of when nuclear physics really began, and in the 30s, an Italian physicist, Enrico Fermi, explored what happened when uranium, and uranium is the heaviest natural occurring element, and he looked at what happened when uranium was bombarded with neutrons. And those neutrons could go into the nucleus, things would happen, and he was hoping that one of the neutrons would stick there and convert uranium into a not naturally occurring element. These were very difficult experiments that required very careful analysis of the chemistry, different element, different chemistry, to identify what was going on. They were hoping to find something heavier than uranium. And in the late part of 1938, at the Kaiser Wilhelm Institute for Chemistry in Berlin, two chemists, Otto Hahn and Fritz Strassmann, they did their analysis and they found barium. Barium is lighter than uranium, and they had no idea where this came from. About a month later, some theorists one of them was in Sweden, Lisa Mittner, and her nephew, Otto Fisch, they did the analysis and they explained what was going on. They realized that what was happening, and I might have to put the mic down, was that the nucleus absorbed the neutron and then it started wobbling. That nucleus was sliding in and out, up and down, around its sort of center. And the uranium nucleus is almost too big to exist, to hold itself together. And eventually, the parts of the nucleus got so far apart, they separated into two almost equal lighter elements. That was the barium that Hahn was seeing in his experiments. So what we had was a heavy nucleus breaking up into two lighter nuclei, and in that process also releasing some energy. And it was a lot of energy because of Einstein's famous equation, E equals mc squared. Shortly after, scientists who knew about this, they realized that this process of nuclear fission, and it was named fission after the biological process of a cell dividing into two new cells. They realized that that energy, if you had enough uranium atoms, could make a weapon of immensely destructive power. It was an atomic bomb, just in theory at that point. So this was the beginning of 1939. By the middle of 1939, physicists in England were so concerned that they authored a letter, Leo Szilard, and he had Einstein sign it, because Einstein was very famous. He addressed it to Franklin Roosevelt, the president, and encouraged him to study this, to see if it was possible to make such an atomic bomb. Similar work has been done in Britain and also in Nazi Germany. Many of the early physicists in nuclear physics were German and Eastern European. So that's August 39, September 39, the Nazis invaded Poland, and we all know where that ended up. So it continues. Everything happened so quickly back then. In early 1940, US physicists found that it wasn't all of the uranium that went through this fission process. It was just one part of it. It's called uranium-235. The 235 is the number of protons and neutrons in the nucleus. you can add more neutrons, it's still the same element, it's just heavier or lighter. Now, uranium-235 is less than 1% of naturally occurring uranium. The rest, it's called uranium-238, it's got 3 extra neutrons. It can absorb those neutrons and create new elements. Neptunium, which is 93 protons, and plutonium. More about plutonium later. So, shortly after that, Otto Frisch, he had escaped Nazi Germany, he was working in exile in Britain. He calculated that as little as 1 pound of this uranium-235, if you could get a pure piece of it, would support an explosive chain reaction. And a chain reaction is the uranium nucleus breaks up into barium and it releases some neutrons. Those neutrons can hit other uranium nuclei, break them up, produce more neutrons, which is it goes on and on and on, consuming all of the uranium and producing a huge amount of energy. Ooh. Yep. So that was 1940. 1941, physicist Glenn Seaborg at University of Berkeley confirmed that the first elements beyond uranium, this neptunium and this plutonium, were created. He did chemical analysis, and he further found that plutonium-241, again, a few extra neutrons, would fission just like uranium-235. That was a second possible path to make an atomic bomb. End of 41, Japan attacks the US. The US enters the war against the Axis powers, and in early 1942, President Roosevelt authorized the development of an atomic bomb. By July of that year, the British agreed to share their research and what they developed with the Americans and to work jointly to build a bomb. So that was early 1942. In August, the so-called Manhattan Project was authorized, and it coordinated all of the work being done on the atomic bomb. So this was mostly an industrial project. They knew what they needed to do. It was just how they would get enough uranium-235 or plutonium to build the device. Brigadier General Leslie Groves from the Army Corps of Engineers was in overall charge, and he appointed Robert Oppenheimer as head of the Los Alamos lab, which just designed the atomic bomb. The production of everything was handled elsewhere. So we have uranium-235, it could support a fission reaction, but it was 0.7%, a tiny fraction of natural uranium. You needed pure uranium-235 to make an atomic bomb. We also had plutonium-231. It could support a fusion reaction, but it had to be created from uranium, and at the time, the amount of plutonium-231 in existence could fit on the head of a pin. They needed pounds of it. Fortunately, maybe, natural uranium, with its 0.7% of that fissionable uranium-235 isotope, it could support a self-sustaining chain reaction slowly. It didn't explode, it just produced energy. We use it now in nuclear power plants. But more importantly, it made a huge number of neutrons. Those neutrons were absorbed by the other uranium-238, and if you took that fuel rod out of the reactor, chemically processed it, you could produce large quantities of plutonium-231. Of course, to do this, you needed what were called slow neutrons. They're moving very slowly, and so you need something to slow the neutrons down, and so they used carbon in the form of graphite around blocks of uranium. By December of 1942, the first nuclear reactor was operating at the University of Chicago. It was in the squash courts under the football field. These are the things you learn in nuclear physics. So the reactor provided the neutrons to turn uranium-238 into plutonium-231. So here, there were two ways. You could do the uranium path or the plutonium path. Neither was guaranteed to work. You couldn't guarantee you could either separate enough uranium-235 or produce enough plutonium-231. But the British and the US, they believed Nazi Germany was working on a bomb. And they were terrified that Adolf Hitler would use it if he developed one. So the US, being the US, said, yep, let's do both. They developed an enormous research and industrial facility. One was in Oak Ridge in Tennessee, and it was designed to separate uranium-235 from the mostly uranium-238. In fact, they tried 3 approaches to do that. They had giant magnets that would separate it because the 235 was slightly less massive, less heavy than the uranium-238. So you bend it in a magnetic field, they land in different spots. The other approach is when you turn uranium into a gas, and then you push that gas through nickel plates with tiny little holes, and the lighter uranium-235 goes through a bit easier. It's very slightly enriched on the other side of the plate. So you take that slightly enriched, and you do the same thing. And then you do the same thing. And you repeat this process tens of thousands of times to get 90% enrichment of this uranium-235, which is enough to support a fission reaction that happens incredibly fast. So that was the uranium path. For the plutonium path, they built a dozen or so nuclear reactors in Hanford, Washington, and chemical processing plants to take the fuel rods, chemically treat them to separate the plutonium, find the plutonium-241, and get enough of that to build a bomb. Turns out that both paths worked. And so we've got these 2 different paths to build a bomb, 2 different materials. Now, you need, for that critical fission reaction to occur, one fission creates a neutron that hits another atom, which creates a neutron, which hits more and more. You need just enough uranium-plutonium to cause that second reaction, and third and fourth and so on, before all the neutrons have left the volume of uranium or plutonium. And this minimal amount is called a critical mass. I mentioned that Frisch had calculated about a pound would do it. This was back in 1941. The British at that time realized how important this information was, immediately classified it. And Frisch, being a foreign national, was no longer able to read his own research. Military intelligence for you. So you've got to get critical mass together. You can't begin with that because it goes bang. So you need to separate them and then have them come together when you want the device to work. So the uranium bomb was straightforward, I guess. You took 2 subcritical pieces of uranium-235. You took one of them, fired it from a gun into the other, so that the net result was bigger than the critical mass. They almost couldn't get it to work, not technical reasons, they just realized the gun they were going to use would be too heavy. You couldn't put it in a bomb. And then someone said, oh, we only have to fire it once. We can make it much smaller than a gun which you fire thousands of times. Plutonium was way more complex. It would naturally fission, and they realized in experiments at Los Alamos that natural fissioning would happen so quickly that as the pieces got close enough together, they'd sort of release enough energy to push them apart again before you reach that critical mass. So, and that happened faster than a gun can fire two pieces of metal together. So they had to develop an entire new process called implosion, where they took a just subcritical mass of plutonium, surrounded it with explosives, and then the shockwaves from those explosives pressed everything together so that it was now small enough that fission would occur. This required incredible testing, planning, and design so that the explosive shape was just right to create a perfectly spherical shockwave to compress the plutonium. And that happened much faster than a gun would fire, so it worked. So they had these two processes. Making plutonium apparently was easier than separating uranium. So there was, by the middle of 45, there was enough plutonium to make two devices. So they built one, tested it in Alamogordo Desert in New Mexico, and it worked. That was the Trinity test, the first nuclear explosion on Earth. The uranium device, that was at the same time put on the US Indianapolis and sent to Tinian Island in the Pacific to be used against the Japanese. After the Trinity test, the other plutonium device was similarly sent, and that was the device used 3 days later on August 8th on Nagasaki. The end. So, happy to take any questions that people have. I know there was a whole lot of stuff in there, so please. Yes, Jim. And you're close enough. Right into the mic.
How soon in the process did the Russians start to get wind of it?
Right from the beginning. I mean, Russia's physicists were, quote, just as smart.
We're going to want you to repeat questions for this microphone too, so just
sorry.
repeat them all.
Okay. So the question was, how soon?
Both microphones.
How soon did the Russians know about what was going on? And the answer is immediately. One, the Russian physicists read the literature and they knew about fission. They knew they could do the calculations and go, we can make a bomb. They also had a number of both spies, Russian agents working in England and the US, but also some of the people involved in the project felt that if Russia, as an ally of the British and Americans during the Second World War, should be informed, they also thought that if we don't tell them, they'll just go ahead and do it anyway. So there was this mix of espionage and also, in some sense, pacifism. They wanted to prevent a nuclear arms race after the Second World War.
Questions? Raise your hand and we'll try to get to them all. I do have a question for you. So this was an interesting movie in that, you see a lot of scientific documentaries. You don't see Hollywood necessarily taking on the story of scientists very often. And this was a movie where, if you've seen it, Robert Oppenheimer, as played by Cillian Murphy, is naked for like 5 minutes at a stretch. I'm curious to hear, did scientists have any reaction to the portrayal by Hollywood of Oppenheimer's story?
So the question was that the actor portraying Oppenheimer was naked during the movie. I would first note that physicists are occasionally naked, not just Robert Oppenheimer. I honestly have not thought about that question. It didn't bother me, if that's what you're worried about. With the movie, I won't give away the ending. But after the war, Oppenheimer was responsible for the design or supervising all the scientists and engineers designing how an atomic bomb would work. So he coordinated everything. He also had, prior to the war, interest in communism. You know, because it was it was different than the capitalist West, and up to the Second World War, the golden age was the rich taking from the poor in the Western democracies. So, like, yes, like now, Susan. Inside voice. So so there was interest, but that gave cause to thought. He was almost removed from the project, but he was also vital because all the scientists trusted him. Immediately after the war, political machinations, and that's what the movie's about, removed his security clearance. He was not allowed to learn anything about the atomic bombs that he was partly responsible for developing. So it was again, the politics of the time, the anti-communism.
Right there.
Germany had quite a head start on every other country. Comment on why the Germans didn't get there first.
So the Germans had a head start. Fission was discovered in Berlin, literally, the heart of Nazi Germany. And why didn't they get there first? That's a really good question. They did work on it, but only as a source of power. They didn't realize that an atomic bomb, well, they knew atomic bomb in principle could work. They just couldn't see how to get there. One explanation I know of is when they tried to develop a reactor, as I mentioned, you need to slow the neutrons down. The Americans used graphite, carbon. The Germans tried it and it didn't work because their graphite wasn't as pure as the American. It had another element called boron in it, and boron is really, really good at absorbing neutrons. And so they couldn't get it, they just literally couldn't get it to work. There is another way to slow the neutrons down. You need something lighter. Water, hydrogen's fantastic, except hydrogen also absorbs neutrons. Unless you have hydrogen that's already got a neutron in it, it's called heavy water. So they did try and build nuclear reactors. They had lumps of uranium suspended in heavy water. It was all supervised by the German post office. As I said, you learn an awful lot doing nuclear physics. The other explanation is that the German physicists didn't want it to happen. No. They stayed in Germany because they were nationalists, I don't think they were Nazis per se, but our country, right or wrong, was sort of the mentality of the time. Many physicists did leave Eastern Europe, surprisingly, mostly Jewish. They ended up very happily working on the Manhattan Project. Terrified that Hitler would get there first. And there was a question here.
So how much was the public aware before the test desert and after?
So the question was, how much was the American public aware? And other than the spies and the people passing information who were working at Los Alamos and other places, they weren't. It was kept incredibly secret. The Corps of Engineers was very careful about shipping things. All the scientists was basically arrived from different routes and that, so it wasn't obvious. And the reason they picked Los Alamos is it was literally in the middle of nowhere. So there was no one around. I believe when the Trinity test occurred, it's a few hundred miles from Albuquerque. People sort of woke up surprised by this brilliant flash of light. And there was this, arms depot blew up or something like that. So it was kept incredibly secret. Of course, Stalin knew about it, And after the first bomb was dropped on Hiroshima, they told Stalin, who said, "Oh, incredible, he knew about it all before." So,
Raise your hands for questions, and right here, ma'am.
Going back to the question about the Germans, Niels Bohr and Heisenberg, that's my husband over there. He's a nuclear physicist. We went to see Oppenheimer. It was a wonderful play. And what about Bohr and Heisenberg? How interesting are they?
so the question was about Niels Bohr and Heisenberg. Bohr was a Danish physicist. He had no part of it. He was held in occupied Denmark, but didn't do anything. The British eventually evacuated him in a secret mission. Heisenberg was one of the developers of quantum mechanics, and he was involved, but again, they did not make progress, partly due, I think, lack of funding. It was the post office, and partly perhaps because they didn't really want to do it. So they did just enough to, I guess, not be sent to the front lines. Yeah. Yes?
The movie hints at, but doesn't really develop how hydrogen bomb came after the atomic bomb. Can you talk about that?
Sure. So the question was about the so-called hydrogen bomb. That was actually very quickly realized as a possibility. Pretty much after the discussion of fission, Edward Teller really wanted that. He was a Hungarian emigre who moved to the US, very anti-Nazi, build the biggest bomb you can. They called it the super. A nuclear bomb works by, you take a heavy element like uranium and break it up into two lighter elements, and there's a tiny difference in mass, and that mass gets converted to energy equals mc squared. You can do the same thing the other way. You can take light atoms like hydrogen, fuse them together to make a slightly heavier element, so you can turn hydrogen into helium. That releases more energy, but it's a much more difficult process. So everyone said, yes, the super will work, but we don't want to waste our time developing it. That continued at Los Alamos after the end of the Second World War, and 1954, I think, the first hydrogen bomb was detonated. It was, yeah, much, much bigger.
Where does the barium come from that's used in medical procedures?
Oh, the question was about the barium used in medical procedures. It comes from mining. It's not from nuclear fission or anything like that.
I thought you meant you created a new element called barium.
Oh no. Yeah, barium is a naturally occurring element. It's lighter than uranium. And since the 1940s, the idea of making heavier and heavier elements by adding neutrons. I think I mentioned earlier that the uranium nucleus is almost too big to hold itself together. Anything heavier than that is too big to hold itself together. They undergo what's called natural or spontaneous fission. Neptunium and plutonium, we don't have any on Earth because whatever was created in stellar explosions and supernovas, etc., has spontaneously fissioned till there's literally nothing left. You can keep going. I think they know up to element 119, which has 119 protons and too many to count neutrons probably. And it lasts for fractions of a second. So you can make these, you can study them, but they're artificial at one level or another.
Let me also emphasize that France is always willing to take scientific questions about a great many topics. But let me also say, we have a bunch of big poles and bars here, so if you feel like we're not spotting you, wave, you come up and grab us. We're happy to take questions from any point of view. You, sir.
Why did Roosevelt pick Oppenheimer, who was then at least hated as being
So the question is, why did Roosevelt pick Oppenheimer to lead the Los Alamos lab? It wasn't Roosevelt, it was Leslie Groves, who was the director. And I think Leslie Groves probably mistrusted the communist leanings in his early life of Oppenheimer, but he also recognized that Oppenheimer was a brilliant organizer, and perhaps equally as important, he had the trust of all the other scientists involved in the project. And I think they needed that because this initially was a race. They thought they were racing the Nazis to build an atomic bomb. They wanted to get there first because they knew Hitler would use it if he had it. But you had a bunch of people who, I don't want to say they didn't naturally work well together, but they just needed to work hard and fast and all the time because they were in a race.
What happened to all the scientists that worked on this bomb and after the fallout, literally, sorry, but after the fallout from what had happened in Hiroshima and Nagasaki, how did they all come to view what they had created?
Okay. So the question was, what happened to all of the scientists who worked on the Manhattan Project, and how did they feel after the bomb was detonated and the destruction of Hiroshima and Nagasaki? I think that's a difficult question to answer. I think most of them were guaranteed funding for the rest of their research lives. I know certainly the guy who assembled the Trinity device was. I think the feelings were mixed. I mean, part of it was, they were pleased that they were successful, because as a scientific achievement, they managed to accomplish this. I think they were torn about the ethical questions. Certainly, there's a famous quote from Oppenheimer from an Indian, not novel, but an Indian legend. I have become death, the destroyer of worlds, after the Trinity test. I mean, very poetic, somewhat accurate as well. So I think it's mixed. I think they were pleased, proud even of their achievement, but there certainly were concerns about the ethics of one using it. Many of the scientists objected to that. Some of them suggested that the first bomb should have been like a demonstration dropped on a tall mountain in Japan and kind of, yep, see, surrender now or we will use it. The other side is more people were killed in the firebombing of Japan of Tokyo by just regular incendiary bombs. Similarly in Europe, Dresden is the big one, the first firestorm the British created. So, to quote someone, war is hell. I think the military just viewed the atomic bomb as a big bomb. It just was bigger than that they already had. And I think more people had died in regular bombing than were killed in the atomic bombing.
Back there, ma'am.
Yeah.
Are they concerned that the chain reaction would destroy the Earth?
So the question was, were they concerned whether the chain reaction would destroy the Earth? And there is, it's in the movie. It was a concern that that somehow the fission reaction would cause a conflagration in the Earth's atmosphere, causing the oxygen and nitrogen to fuse and destroy the Earth. It sounds silly, but they did the calculations and decided that the theory suggested that was incredibly unlikely. I guess obviously it didn't, so we're all good. Yeah. Yes, ma'am.
What now, when we have Putin threatening to use nuclear weapons in Ukraine and against the British, and of course we have enormous arsenals? What do you think now?
So the question is, what now with nuclear weapons? I mean, the Americans and the British worked together. They were the first nuclear armed powers. The Russians had, through espionage, basically learned everything from Los Alamos. So 1947, they detonated their first atomic device way sooner than the American military intelligence thought. After that, the French didn't want to be left out, so they developed their own nuclear weapons. So those 5 nations, they're the 5 permanent seats on the UN Security Council because they had nuclear weapons. Yes. After the war, a lot of countries, quote, wanted to be there. I think I did mention, you can make a nuclear reactor with uranium-235. The Americans do that for their submarine power plants. You can make a uranium reactor with natural uranium, but you've got to use heavy water. And so the Canadians developed a heavy water reactor. It's called the CANDU, the Canadian Deuterium Uranium Reactor. And it was explicitly designed for peaceful purposes to give, nuclear power to nations because you couldn't use it to make plutonium. So the Indians did that and used it to make plutonium. So that's how India got their bomb. The Pakistanis didn't want to be left behind, so they did industrial espionage against the French to learn how to make devices to enrich uranium. I can't remember his first name, but the physicist Khan, he basically did industrial espionage against the French isotope separation, and that's how India got the bomb. To pay for it, they sold their technology to North Korea and Iran and Iraq. Hey, you got to make your money somehow. The Israelis have a bomb. They worked with the other pariah nation of the 1960s, South Africa. They did a test somewhere in the South Pacific. South Africa is the only nation to give up a nuclear capability. Ukraine gave up weapons, but they were Soviet weapons stored on Ukrainian territory, and they gave them up in the promise from all powers, including Russia, that their territorial integrity would not be violated. Are we safe? Not absolutely. Not absolutely. I mean, it's been over 70 years, and other than Hiroshima and Nagasaki, they have not been used in war. People have threatened, but they've not been used. I think that 1960s mutually assured destruction, if you bomb me, I'll bomb you, back to the Stone Age, has held. Whether that continues to hold with nations like North Korea, Iran is, depending on who does the calculations, a year to a month away from getting enough enriched uranium to build a bomb. Other nations with industrial capacity could. Japan, Australia, Germany, most of the Western European countries have the technology base to develop an atomic bomb, but they have not. So anti-proliferation has worked to some extent, but yeah, they're bad things.
At the bar, sir.
Please comment on
So the question was to comment on Chernobyl. The Chernobyl reactor design was a graphite moderated natural uranium reactor. It was the Russians' design to make plutonium. It's really easy to push the fuel rods through. They never modified their design because it worked for them. And to demonstrate how much better they were than the Western Europe, they were so assured of their safety standards, they never built a containment vessel that every Western nuclear reactor has. So when Chernobyl happened, there was literally nothing to stop the release of radioactive material. To be fair, they did have very good safety standards. The only problem was they wanted to do a test of could they use the residual power, the residual spinning of the generators to generate enough electricity to continue the cooling pumps until the backup diesel generators kicked in. And they wanted to do the test, but the test kept getting delayed because they were doing it when a reactor was naturally shutting down. So the reactor safety systems wanted to shut the reactor completely, and they kept bypassing all the safety systems. Someone described this as, if this had happened at like in Europe or America, the computer system would have shut the reactor down, locked the doors, and called the police. Yeah, Chernobyl was a terrible disaster, and it was one, stupidity on behalf of the operators, but also just they did not build a containment vessel. They just assumed nothing bad would happen.
I'm waiting for our nachos to take.
Grant, let me ask a question of you. We've talked a lot about other folks' research. We haven't talked much about your research. Is there a question that from your research that you would love to have an answer to, or a next question that you'd love to answer?
Oh, God. There's so many. One piece of research I did several years ago was we understand forces, how the universe works in terms of forces and in terms of particles interacting with one another. And we always assume that one particle interacts with another, and there are always these pairwise forces, and you just add them all up and you get the answer. In the nucleus, that doesn't work, because you can do all your calculations, and they work fine for atoms which have 2 particles. But when you get to 3 particles, uranium has 238. But when you get to 3 particles, your calculations no longer work. You need to include the effect of what we call a 3-body force, where 3 particles interact with one another separately and differently than the individual 2 pairwise forces between all those particles. That's for 3 particles. We can do 4 kind of with enough computer power. After that, it's a mess. So yeah, 3-body forces is one of the research projects I did.
That sounds like a great title for an HBO show. I'm sure Grant is happy to keep taking questions here, but I did want to take a chance to give him a second to catch his breath and have a sip of water here and say, first of all, thank you again to Last Round for hosting us here today. They always do a fantastic job. Thank you to Ann Parson, who organizes these science cafes and leading the steering committee. I hope you pencil it on your calendars for Tuesday, May 7th is our next science cafe. We're going to have Westport farmer Bill Braun and local horticulturalist Hannah Tragus. They're from the Freed Seeds Federation, and their talk is going to be called Saving Our Seeds. So that's again on Tuesday, May 7th. I'm sure Grant is happy to keep taking questions. So any other questions here?
There was one
back there.
So the question was, during the Cold War, there was a fear of what was called a nuclear winter, where if there was a nuclear war, it would put so much dust and debris into the atmosphere that it would reflect the sun's light and the Earth would go into another ice age. And so more recently, there's the fear of artificial intelligence, and that could, be the end of civilization. I think we have these existential threats all the time. AI is just one of the most recent. Where that's going to go, that is way outside my field of expertise. And it would be nice if we could find someone to give a talk on that at some point. And so, yeah, I think every generation has its existential fear. I mean, I'm old enough to sort of remember the fear of nuclear war when I was in what the equivalent of elementary school in Australia. The French were still doing atmospheric tests in the South Pacific, and there was huge protests on that. And so that was a fear. I remember marching for nuclear disarmament. I think every generation has a particular fear. Nuclear winter was one. More recently, it's been climate change. Artificial intelligence is just the latest of those things. And I think we need to know about them, we should be aware of them, we should be thinking about them.
Other questions? Sure.
As a young person, how did you become interested in nuclear physics?
How did I become interested in nuclear physics? I always wanted to. I had the How and Why book of nuclear physics, which was about the discovery of nuclear fission. I still remember that. And so, I literally always wanted to be a nuclear physicist. Yeah, I was a strange kid.
Any other questions for Grant tonight? Grant, thank you.
Well, thank you, everyone.